In this video we're going to work with another volume of revolution. This time we're going to work with a solid that is formed by revolving the area between two curves about the x-axis. And the curves that we're working with are f of x equals x squared and g of x equals x cubed. So if that's a picture of x squared, then this is a picture of what x cubed might look like. We know that the two intersect at x equals 0 and x equals 1 based on our simultaneously solving those equations, giving us two solutions, one at x equals 0 and one at x equals 1. Now, if we chose a value in between, interior to that, to those 2 points of intersection, for example 1/2, and we evaluated x squared at 1/2, we would get 1/4. If we evaluated 1/2 at x cubed, we would get 1/8. So in this case, x squared is above x to the third. And what we want to do then is to take that region enclosed between the two graphs and spin it around the x-axis. And when we do, we're going to form this funnel-shaped object that looks like a funnel on the outside, but kind of has a little thickness as you move in from the top on the inside. And so if you were to slice it perpendicular to the x-axis, to take a thin slice of that, you would have a washer. And the surface area of one of those washers would look something like this, where we have a little radius, the hole of the washer, and a big radius, the outside of the washer. And so the surface area of this washer would be the area of the big circle minus the area of the little circle, or pi capital R squared minus pi little r squared. And the thickness of that washer would be, since that thickness is a change in x, would be our dx. So we can then measure the incremental volume of one of those thin slices of the solid, which is a washer, and that would be dV. It's an infinitesimal change in the volume. And that would be pi times the quantity capital R squared, which is the radius of the outer circle, and that is x squared, since x squared lies on top there. But we want capital R squared, so we need x squared squared, which is to the 4th power, minus little r squared. And if little r is x cubed, then little r squared would be x to the 6th power. And the thickness is given by dx. So that would be the formula for an incremental amount of volume added by one of those sliced washers. The entire volume would be given by pi times the integral from 0 to 1 of x to the 4th minus x to the 6th dx. And so we have completed setting up the problem, and the rest is straightforward. So we have pi times the integral from 0 to 1 of x to the 4th minus x to the 6th dx. And the antiderivative would be x to the 5th over 5 minus x to the 7th over 7, evaluated from 0 to 1. Of course, all multiplied by pi on the outside. We want to evaluate x to the 5th over 5 minus x to the 7th over 7 at 1, and that just gives us 1/5 minus 1/7. But then evaluating that expression at 0 just gives us 0. And so we end up with 1/5 minus 1/7 times pi. Using a common denominator of 35, we would end up with 2/35 pi, or 2 pi over 35. So once again, this is an example of revolving a region that is bounded by two graphs, or enclosed between two curves about the x-axis. And that does it for this video and this example.